So we're still working on fluid dynamics problems. So if you haven't checked the playlist, please check the playlist. There are a couple of interesting problems that I believe you can benefit from. So let's just attempt the question. So if incompressible, telling us that the whatever, let me say x, whatever is interested in, but as long as you differentiate pressure, you're going to get 0, or there's just not, as you go along x, then viscous fluid is placed between two parallel infinites, two plates, and there's fluid going in this way. So two plates move in opposite direction with constant velocities. These are velocities shown. The pressure gradient in x direction is 0. They already gave us that, right? Oh no, pressure with time is incompressible. Then this one is telling us that pressure as I go to x also should be 0. Only the body and the only body force is due to fluid weight. Use Navier-Stokes to derive expression from velocity distribution. Okay, so you want to see how this thing looks like. We're expecting it to, maybe it should look like something like that. Remember, for the poor, I can't even say the word. Let me just have something on my notes because I can't even. Poisel, I don't even know what to say, but this thing, something like that. We have, most of these names are not really English, so that's why I struggle to say them, because they have their native language I don't even know. So yeah, so that's the word. So don't be interested where the plate is moving. The name of that one is called, let me check my notes, it's quite right. So I think it's better. Here it's plate moving. For pure cell, I don't even know how to say this word, it's going to be pressure difference. So if I have pipe and then there's pressure in and pressure out, the only thing it's making is this thing diffusing to lower pressure. But in this case of quartz, of which we're interested in, I have a plate moving. The plate is the one that is causing fluid inside to move. So yeah, that's the baseline of everything. So we're going to start with our favorite Navier-Stokes. Navier-Stokes equation that says that F is equals to ma. Actually, I like thinking about it like that way because it makes things easier for me. That is that gravity one, that is pressure difference mu, that Laplace term, and v. So this one is it's just vector. So it's obviously in one dimension. It's one dimension. So interested what is going on this dimension. So so let me look at what is going on the u term technically. So on the u term, I'm going to have this du dt plus u du dx plus v first du dx. I want to continue to z, don't make any point, and then we will have to GZ. But before I continue, we do know that this term will be 0 because we don't have velocity along y. So yeah, I think to start my argument very well, I think I have to start with continuity. So every time you have to derive this, I think continuity is the first thing that you need to look at. Continuity, we say that this and that plus this over y should equal to 0. So we already know that we don't have these two, right? We already know this one will go to 0 because we literally don't have them. So du over dx will have to equal to 0. Let me call that on 1, right? Du dx. So this one is obviously dying. This one is dying because we don't have it. This one is dying because we're saying it's steady, right? So this one we ignore, plus mu. So I think the main trick here is explaining why every term disappears, right? Then now first is going to be du dx squared. This one, if this one is that means also this one will die again. So this one is equal to 0, c1. Go and check what I said at 1. That's what I said. Then plus du squared all over dy squared. Okay, we didn't say anything about that, but du over dz doesn't exist also. So that makes us have this term. That's only term that remains after I check on my, we call this guy, my Navier-Stokes. Okay, so I'll have 0 is equals to this. This is what we end up having. So what funny is that most of the time, if you're doing Poiseuille or Couette, what do you call it? Couette flows, this is the thing that you end up with. So some people can just dive into this, bring this, but I feel like I like you explaining every reason for every term to die before you just cancel them, right? Just, I don't know, for some reason I think it's the right way. So let me say I have du dy. I need to differentiate it again, right? In terms of y, for me to say it equals to 0. To cancel everything, I do what mathematicians don't like, of just integrating everything like this. I know most people are not a fan, but yeah, just a quick way of writing it. You know that I'm supposed to do it like both sides, but it's all over, isn't it? Then this thing will cancel that, then I'll end up having du d y here. Differential is then can undo, integral the other way around also. Then I'm going to get my first constant. Then I'm like, okay, why not again? Then we do it again. dy integrates everything that is here. I literally mean integrates both sides if I do this sign. I know it's not mathematically, but I've never seen a mathematician like it like this, write it like this, but I like it anyway. Then I'll have u here. Then here I'll have to get c1 will get an x, a y, sorry, and we'll be adding some, because these are partials, we're not getting to get a constant, do we? Yeah, it is a constant actually. It's going to be my, we don't get a constant when we're doing those streamlines and everything. We're going to get another constant. Right, now we have a formula that actually tells us about how it's actually telling us, as I move from plate A to B, how is my u changing? Is it increasing or decreasing? It doesn't look linear, so we expect them to look like this. Maybe if there was some sort of pressure going in, it would have been bent a little bit. So it doesn't matter that much, but this is what we like. The only thing that remains here are boundary conditions. Boundary conditions, where do I get them? I get them from here, right? This is y, right? Let's say when y is equal to 0, our u is u2, right? Did I say these u's are the same? Let's check. Okay, opposite direction, but it's u. But let me call it negative since it's the other way around. All right, so negative u2, but u2 actually hold for, it also has direction in it. u2 will be fine, is equal to c1 when y I need to say y when u at y is equal to 0. Yeah, that's how it should look like. Then I can put a 0 here plus c2, then my c2 equals to y2. Yeah, that's my boundary condition 1. Boundary condition 1. Let's look at our boundary condition 2. That one will be us saying what is happening here on top, right? So we'll have to have our y equals to b. Okay, let's see. What is going to be u if I put y equals to b? It's one of those things mathematicians don't like, but I do it anyway. It's going to equals to u1, right? And then plug into that equation. It's going to be u1 is equals to c1, and then y here is equals to b plus, what's the other one, c2. We already know c2, by the way, so I think it's best that I write it as y u2. Then c2 is equals to c1, this one, is equals to u1 minus u2 all over b. So we already have this constant. So our y, sorry, I need to go back to pen. Y is going to equals to y u1 minus u2. I feel like it should have been that way, but I think if I made a mistake, you can find out when you do it that maybe I didn't do something right. Then I'll have a y here minus y plus u1. So this is a linear function, right? Okay, let me just draw the graph. This thing's supposed to look like this. So when I make this thing 0, I'm supposed to get something that is negative. So I think that's why I have to make this number negative. The other one, this one. Because if I make this guy 0, I need to get a negative velocity. So it's not entirely the way I draw it. I think this represents it better. We'll have u, I don't know, it was u2. I think it was, yeah, it was u. It was u1 or 2? Okay. On my thing, I think it's called u2. Then u1 being that one. Is it? u1 is on top one. Look like that. Yes. Then yeah, and the slope is positive. You can see this thing is positive. Yes. u1 is the, yeah, minus make this thing positive, and this is positive, and from there to there, that's your p. That's, I'm trying to interpret it with like your line graph. So I think now you've ended up with a beautiful conclusion. Thank you.